Hello everyone, Funda Sonke here. Today we're going to be looking at grade 12 physical science question and answers, and the topic is as given below. Remember to subscribe and follow us on Instagram, Facebook, and Twitter. Okay, our first question today. A box of mass 100 kgs slides down a rough slope, which forms an angle of 30 degrees to the horizontal. The friction that acts on the box is 20 newtons. Draw a free body diagram representing all the forces acting on the object and calculate the resultant force acting on the box, causing it to slide. Perpendicular forces may be ignored. We're going to start by drawing a force diagram. Okay, we're told that the inclined plane forms an angle of 30 degrees. You've got a mass of 100 kgs. Then associated with that mass is going to be a weight which acts vertically downwards. Due to the force of gravity, so we're going to call this Fg. Okay, then we are told that there is friction that acts on the box, and the friction is 20 newtons. Since the mass is going to slide down the rough slope, which is in this direction, it means that our frictional force will act parallel to the surface in the opposite direction. Okay, of which this frictional force is 20 newtons. Okay, now since this box is on a surface, it has got a normal force acting perpendicular to the surface. Okay, then the next step is to resolve the vertical and horizontal components associated to the weight or the force due to gravity, such that you're going to have a component which acts perpendicular to the surface, and this component will be equal to the normal force. Then we'll have another component which acts parallel to the surface downwards along the slope. Okay. So therefore, this component described by force due to gravity, which is perpendicular, while the one acting along the surface given by force due to gravity parallel, and the vertical force perpendicular to the surface is our normal force. Okay. Now, since we know that our force due to gravity or weight which is equal to our force due to gravity is basically your mass multiplied by your gravitational acceleration, g. And therefore, to resolve the components associated with the weight, we then have our F due to gravity perpendicular being equal to our force due to gravity cos theta, while our force due to gravity parallel to the surface will be equal to our force due to gravity sine theta, where theta is the angle of inclination, in our case, our 30-degree angle. Okay, so since we have now drawn our force diagram, the question says we need to draw a free body diagram. So therefore, our free body diagram would look like this. We'll have a force acting along the plane and a frictional force acting in the opposite direction. Then we'll have a force perpendicular to the surface, and then the normal force acting in the opposite direction, like that. Okay, where in this case then we can label each force Fg parallel, like that. This is Fg perpendicular, and this is our frictional force, and this is our normal force Fn. Okay, now since we are told that the mass is going to slide down the surface, therefore it means the magnitude of our Fg parallel is much greater than our frictional force. That's why you see that the arrow for our Fg parallel is longer than the frictional force. Whereas our vertical components or perpendicular forces are in equilibrium. Therefore, you find that your normal force is equal to your Fg perpendicular. Hence, the length of the two arrows representing the normal force and Fg perpendicular will be equal. So this is how your free body diagram looks like. So there's a difference. The first diagram is a force diagram. The second diagram is the free body diagram, which they asked for in this question. Okay, so the force diagram was there so that it can help us to have a clear picture or an understanding of what the free body diagram would look like. So normally I'll draw the force diagram first, which gives me a description or an illustration of the scenario being described. Then I move on to then draw the free body diagram, which is represented by these arrows there. Then on the free body diagram, you also need to then include the angle of inclination. In this case, I'm going to use theta will be equal to 30 degrees. Okay, then you can write here that it is the angle of inclination. Okay, so we've answered the first part where they want the free body diagram, which is that there. Then the second part is they want us to calculate the resultant force acting on the box, causing it to slide. Perpendicular forces may be ignored. So they've told us that we can ignore the perpendicular forces. So we're not going to consider Fn and Fg perpendicular. Instead, we're going to take into account the force due to gravity parallel acting along the surface and also the frictional force, such that then our F net will be equal to our Fg parallel plus our force due to friction. Okay, of which we know that Fg parallel is given by force due to gravity multiplied by sine theta. So this will be equal to force due to gravity multiplied by sine theta plus our frictional force Ff. Okay, then this will be equal to our gravitational force, which is 100 kgs. This is multiplied by our acceleration due to gravity, 9.8. This is meters per second squared, sine 30 degrees, plus, in this case, we're going to take the direction of motion as the positive direction. So it means the frictional force acting opposite will be negative. So this will be plus minus 20 newtons. Okay, so then if we were to calculate that there, we'll find that we're going to get 490 newtons minus 20 newtons. This then will give us a resultant force of 470 newtons. Down the slope. Okay, so we're done with our first question. We're able to calculate the resultant force or the net force, and we're able to also draw the free body diagram. Now, our next question. R and S are two positively charged spheres. P is a negatively charged sphere. Sphere R exerts an electrostatic force of 0.2 newtons on P, and sphere S exerts a force of 0.6 newtons on P. Draw a free body diagram of sphere P, for sphere P rather, and then calculate the resultant force on sphere P. So we're going to draw the spheres. Just to illustrate. Okay, my sphere may not, or my circles may not be as symmetric as one would want them to be. Okay. Then we are also told now the charges of the individual spheres. So we know that R is positive, so this will be positive. P is negative, and sphere S is also positive. So we know that opposite charges attract. So it means sphere P, or the negative charge will be attracted to the positives. So in this case, you'll have a force acting in that direction and another force acting in that direction. Okay, so I'm just going to label the individual spheres. So this is my R, this is my P, this is my S. Then I'm told that force R exerts an electrostatic force of 0.2 newtons. So this will be 0.2 newtons towards R, while sphere S exerts a force of 0.6 newtons. So this will be 0.6 newtons towards S. Now, since 0.6 newtons is much greater than 0.2 newtons in magnitude, it means I need to then extend magnitude, or the length of my arrow, to depict or to show that this force is greater, and at the same time I'm going to reduce this arrow this side. Okay, so now this is a force diagram illustrating the forces acting on sphere P. But then the question says we need to draw a free body diagram. And remember, with free body diagrams, your object is considered to be a point mass. So hence we only represent each of, or the object under investigation, is just a small point. In this case, you don't necessarily have to draw a whole big circle like when it comes to your force diagram. So a free body diagram, your object is just a point mass. So therefore, for our free body diagram, we're just going to have an arrow acting to the left, representing our force of 0.2 newtons. Then we'll have another arrow acting to the right, representing our force of 0.6 newtons, like that. Then, since we said your object represents a point mass, so normally we just introduce like a small point there, which represents the object under investigation. Okay. Then in this case, we're going to consider the force acting to the right to be positive. So which means the force acting to the left will be negative. Okay. Therefore, the resultant force in this case, which will be our force net, will be equal to our force, positive force, 0.6 newtons, plus the force acting in the opposite direction, which is negative 0.2 newtons, such that then our resultant force will be 0.4 newtons, and this is acting towards S. Okay, now we're going to go on to the next question. Okay, in this question, three identical spheres X, Y, and Z are in the same horizontal plane. Spheres X and Z are both positive, and sphere Y is negative. Sphere Y exerts an electrostatic force of 400 newtons on X, and sphere Z exerts an electrostatic force of 300 newtons on X. Draw a free body diagram for sphere X and indicate the electrostatic forces acting on it. So again, I always like to start by drawing a force diagram before I draw the free body diagram. So I'm going to draw my 3 spheres, in this case, my X, Y, and Z. Okay, I just need to align this with that there, and I need to align this with that there. Then now we need to consider the forces that are acting on the objects, or on the spheres rather. So in this case, this is my sphere Z, which is positive, and here I've got my sphere X, also positive, and there's got my sphere Y. Okay, that's a triple Y. It looks like an X. Okay, my sphere Y, which is negative. Such that my X will be attracted to Y, while Z is going to exert a repulsive force pushing X away, like that, right? Such that then, in terms of free body diagram, remember I said each sphere, when it comes to the free body diagram, a mass or an object is considered to be a point mass. So I'll have a point mass there. Like that. Such that my force of attraction towards Y will be represented by an arrow to the right, while the repulsive force from Z acting onto X will then be a vertical arrow acting vertically upwards, like that. Okay. So then here you have your force Z acting on X. So this I'm going to call force Z. And then you have your force Y force Y acting on X. Okay. So this is how the free body diagram would look like. Then for part 2, calculate the magnitude of the resultant electrostatic force on the sphere. Okay, so in this case, we can see that this is similar to how one would then solve the two-dimensional vector forces. So in this case, we can see that we've got two tails from one point. And remember, from your vectors, you always want to have head to tail type of vector addition. Okay, so for us to then be able to resolve or to calculate the resultant electrostatic force in this case, there are two approaches that one can use. Either you can translate this force acting vertically upwards, the force Z, such that the tail comes to the head of force Y. Or we can translate the force Y so that the tail goes to the head of force Z. So we're going to use the latter case for our illustration here. So what it means then is we've got a force Fz, which is acting vertically upwards like that. Then we're going to translate force Y so that we have our head to tail vector addition, which is that case there. Okay, so in this case, our resultant based from our Pythagoras theorem will then be represented like this. Okay, so that then this is our force. This is our force net acting on X. Remember, this is our force Z, and this is our force Y acting on X. Okay, and we're given the values in this case. We're told that sphere Y exerts an electrostatic force of 400 newtons on X. So this will be 450 newtons. Okay, while Z exerts an electrostatic force of 300 newtons onto sphere X. So this will be 350 newtons. So from Pythagoras theorem, we know that our force net will be equal to our force Z, force net squared will be equal to our force Z squared plus our force Y squared. This then will be equal to force Z squared is 350 newtons squared plus 450 newtons, all of this squared. Therefore, our force net will be equal to the square root of 350 newtons squared plus 450 newtons squared. Okay, I'll have to use my calculator to do that. Okay, 350 squared plus 450 squared will give us 325,000. So then that means is our force net is equal to the square root of 325,000 newtons squared. Okay, therefore force net will be equal to the square root of 325,000. Okay, that will be 570.088 newtons. So that is your resultant force or electrostatic force, resultant electrostatic force acting on X. Okay, so we're going to go on now to the next question. Two boxes, A and B, are lying on a table and are connected by a piece of string. The mass of box A is 3 kgs and the mass of box B is 2 kgs. Assume that the mass of the string is very small, so we can ignore it. A 30 Newton pulling force pointing on the right is applied to box B, causing the two boxes to move. The surface acts with a friction force of 5.9 newtons on box A and 4.1 newtons on box B. Calculate the acceleration of boxes A and B. Okay, so in this case, we've got two objects or two bodies that are attached together by a string. So one can consider the two objects to be a single system or a single unit. such that then what it means is if this is a single system or a single unit, we can then consider the total mass of the system. So our total mass, in this case, we're going to call it M total, will be equal to the 3 kgs, which is box A, plus the 2 kgs, which is box B, which will give us a mass of 5 kgs. Okay, so that is the total mass that we have. Then we are told that now, since this is a complete unit in our case, it means we are going to have a total force pulling towards the right being equal to 30 newtons. In this case, we're going to call this the force applied. So our force applied will be equal to 30 newtons. Okay. However, we also know that there is a frictional force acting on the boxes or on the individual boxes. And in this case, since we say that this is now a complete unit, it means then we can have a total frictional force, which we're going to call small ft, will be equal to, then we add the individual frictional forces, which is 5.9 newtons plus your 4.1 newtons, and this will give us a total of 10 newtons. Okay, and this is acting to the left. So if you consider the right side to be positive, so it means our frictional force acting in the opposite direction will be negative. Okay. So in this case now, I want to calculate the acceleration. Therefore, we're going to then recall Newton's second law, where we know that the resultant force or the net force F net is equal to the mass of the system multiplied by the acceleration. Okay? Such that then from this equation, we should be able to calculate the acceleration because we know what the mass is, it's 5 kgs, and we can deduce the net force by considering the applied force and also the force of friction. So in this case, our net force F net will be equal to our FA plus our F small f t. This then is equal to applied force, which is 30 newtons, positive because then it's going towards the right, plus our frictional force minus 10 newtons, which is acting in the opposite direction, such that our net force will be equal to 20 newtons. Okay, then from our equation, F net is equal to mass times acceleration. We can therefore say 20 newtons will be equal to mass. In this case, it is 5 kgs multiplied by our acceleration, which then implies that our acceleration will be equal to our 20 newtons divided by our mass, which is 5 kgs. Therefore, our acceleration is equal to 4 meters per second squared. Okay, so there we have answered the first part there. Okay. Then part 2, they want us to calculate the magnitude of the tension on the string. Okay. So they want us to calculate the magnitude of the tension on the string. So we can use this by considering the two boxes as individual. Okay. So in our case, we can consider box A. Okay. So we're going to consider box A. However, I can also solve this by considering box B. Okay. So in this case, if you consider box A, we'll then look at the forces that are acting on box A. So if we consider if we decide to use the Freebody diagram to describe those forces, we're going to have a frictional force which is acting to the left like this. Okay. Then we are going to have force from the tension of the string pulling our box A to the right, like that. Okay. And in this case, we know what the mass of box A is, and we have already calculated the acceleration. Okay. So again, if we then consider Newton's second law, okay, let me just complete this free body diagram, because then we're also going to have the weight of the object acting downwards, and then upwards we'll have the normal force. Okay, I'm going to add labels to it. So this is T for the tension of the string pulling box A. Then this side will have our frictional force F. Then you have got the normal force Fn. Then you have got the force due to gravity Fg. And then we know that from Newton's second law, F net is equal to mass times acceleration. In this case, our F net will be equal to, if we take this to be positive, it means our frictional force will be acting in the negative direction. So our F net will be equal to T plus our frictional force Ff, which then will be equal to T minus, in this case, our frictional force acting on box A was 5.9. So minus 5.9 newtons. So this is our F net. Okay. So we're going to substitute this into our equation. F net is equal to ma. So it means that T minus 5.9 newtons will be equal to our mass, in this case for box A is 3 kgs, and this multiplied by our acceleration, which was 4 meters per second squared. Okay, this is 3 kgs, like that, such that then our tension T will be equal to 12 newtons, but then that is 3 times 4 plus 5.9 newtons. Therefore, your tension will be equal to 17.9 newtons. Okay, so you may consider box B and work it out and see if you will get the same answer, 17.9 newtons. Okay. So now we're going to go on to the next question. The sketch below shows a box of mass 8.5 kgs at equilibrium on an inclined slope, plane bracket surface. Okay, calculate the magnitude of the tension in the cord. Then calculate the magnitude of the normal force acting on the box. And then part 3, the magnitude of the box acceleration if the cord is cut. Okay, so like the previous diagrams, in this case, we would want to have an illustration of the scenario that has been described. So I'm going to draw an inclined plane. Okay, like that. And this inclined plane, we're told that, or we can see that this is at 30 degrees. Then we're going to have a mass. That mass is 8 kgs, and it is attached to a fixed wall. In this case, I'm going to draw this to be our fixed wall. Okay, my drawing might not be that good, but we're trying to just show an illustration. Okay, such that now we want to then draw the forces that are associated or that are acting on the object. Okay, in this case, since it is a mass on a surface, therefore we're going to have force due to gravity acting vertically downwards, like that. Okay, and already we've got tension due to the string holding the mass from sliding down, attached to a string attached to the wall, so that will be our T. And then we're going to have a normal force acting normal to the surface. Then we're going to have our components from our force due to gravity, the perpendicular component and also the parallel component. Okay, so we're just going to label those. So this is Fn. This will be our Fg perpendicular, right? This is just our Fg, and then this will be our Fg parallel. Okay, so we've got this force diagram which will help us to answer this question. And the first question is, we want to calculate the magnitude of the tension in the string. Okay, so if we were to look at this question here, we're told that this mass is in equilibrium. So therefore what it means is the tension holding the mass should be equal to the force acting parallel due to gravity. Okay? Of which in this case, we're told that this is on an inclined plane surface. So one can then assume that there is no friction associated with this surface in this case. Okay? So if we're then going to consider that, what then it means is we can then find our tension based on the fact that this system is in equilibrium. In other words, your Fg parallel should be equal to your tension, or the algebraic sum of the forces acting parallel to the surface should be equal to 0. So we're saying now our Fg parallel plus our tension should be equal to 0. And in this case, we're going to assume that the force acting downwards the plane is positive, while the force is acting up the plane to be negative. And from resolving our components, we know that our Fg parallel is equal to Fg sine theta. And also our Fg perpendicular is equal to Fg cos theta. However, for the first question, we are only going to need Fg parallel, right? So for part 1, we can safely say that Fg parallel plus tension is equal to 0. And our Fg parallel is Fg sine theta. In this case, minus tension should be equal to 0, since we said tension is acting in the negative direction. But let us not forget that force due to gravity is given by mass times gravitational acceleration. So it means then we're going to have our mass times gravitational acceleration sine theta will be equal to our tension. Okay, so since we know what mass is, or the mass of the object, it's 8.5 kgs, and this multiplied by our gravitational acceleration 9.8 multiplied by sine 30 degrees is equal to our tension. So if you multiply that, we're going to get sine 30 is 0.5 times 9.8 times 8.5. This should give us 41.95. Oh, sorry. 41.65 newtons will be equal to our tension. Like that. Okay. Then the next question is they want us to find the magnitude of the normal force acting on the object. So now the normal force, remember, takes into account the vertical components. So in this case, we're looking at Fn and also the force due to the perpendicular component of the force due to gravity, which is Fg perpendicular. Okay, so then what it means is for number 2, we're going to have, if we assume that our normal force or upward force to be positive, and in this case, our Fg parallel our FG perpendicular will be negative. So we're going to have our Fn, in this case, minus our FG perpendicular being equal to 0. Okay, since FG perpendicular is negative, that's why I've already included the negative sign there. So my normal force Fn will be equal to, know that FG perpendicular is our force due to gravity times cos theta. So in this case, this will be Fn is equal to Fg cos theta, such that our Fn is equal to mass times gravity cos theta degrees. Okay, therefore our normal force Fn is equal to mass, which is 8.5 kgs, multiplied by 9.81, which is gravitational acceleration, so to be meters per second squared, cos 30 degrees, like that. So then if we were to punch this into our calculator, we find that Fn is equal to 8.5 times 9.81 times cos 30 degrees. This should give us 73.1 newtons. So this is our normal force N. Okay, so that's the magnitude of the normal force acting on the object. Now, the second part, or the third question rather, they want us to calculate the magnitude of the block's acceleration if the cord is cut. So in this case, if the cord is cut, then there is no tension acting on the object. Okay? So in this case, there is no tension acting on the object. And since we want to calculate the acceleration, we're going to consider Newton's second law, where we know that F is equal to ma. Okay, I'm just moving this up a bit to create some space. So we know that our force net is equal to mass times acceleration. And so we are told that if the string is cut, so there's no tension, it means this object will accelerate down due to the force Fg parallel. Okay, so therefore our force net is just Fg parallel, which is given by Fg sine theta is equal to our mass times our acceleration. Okay, which is just our mg sine theta, which is equal to our mass times acceleration. Now, since the masses are the same, we can always divide both sides by mass, such that then we're left with our acceleration being equal to acceleration due to gravity sine theta degrees. So our A will be equal to 9.8 meters per second squared times sine 30 degrees, like that. Okay, therefore your acceleration will be equal to 4.9 meters per second squared, because your sine 30 degrees is equal to half, so half of 9.8 is 4.9 meters per second squared. So that's the acceleration when the string is cut or when the cord is cut. Okay, so this is the full calculation for that problem there. So we've answered the first part, second part, and also the third part. I hope you can see that it is important to always draw this force diagram, because then it gives you an illustration of the scenario that is being described. And from there, you can then resolve the perpendicular and parallel components of your weight. That is, if your block is placed on an inclined plane like that. Okay, so now I want to consider now our next question, which is two blocks of mass 25 kgs and 15 kgs are connected by a light string on a horizontal surface. Assume that the string cannot stretch. Okay? A force of magnitude 240 newtons is applied to the block of mass 15 kgs, forming an angle of 60 degrees with the horizontal, as shown in the sketch below. The coefficient of kinetic friction is 0.2 newtons. So the first question says, state Newton's second law of motion in words. Well, in this case, I'm not going to do that, because then it's something that you can read off your normal grade 12 physical science textbook. And at this stage, I really expect that if you're in grade 12, you should at least know Newton's second law of motion in words. Okay? Then part 2 says draw a free body diagram for each block. Okay, so we're going to do that. But then in my case, like I said, I always find it much easier if I start by drawing a force diagram, because then it gives me an illustration of the scenario being described. Then from there, I can then draw my free body diagram. So in this case, for my force diagram, I'm going to use the diagram that is already there in the question. So we've got a mass in this case, and that mass of 25 kgs and a mass of 15 kgs. So the forces that can act on this mass are, you've got your normal force, which will act vertically upwards. And then you'll also have your weight, which is acting downwards like that. Okay? Now, if we then assume that the right side is positive, okay? You can assume that the right side is positive. So this direction will be positive, okay? So it means we're going to have an opposing frictional force acting in the opposite direction. So we're going to have friction acting in that direction. And now, since we've got a string attached, right, where this string is pulling this 25 kg mass to the right, so it means we're going to have a tension from the string acting towards the right, which is pulling the 25 kg mass. Now, if you consider the second mass or block, in this case, is 15 kg block, again, same thing, we'll have our weight or force due to gravity acting downwards. Then we're also going to have the normal force acting upwards. Okay, these need to be equal in length since they are in equilibrium. So I'm going to adjust the length of this one as well so that it is the same. Okay. Then from there, of course, we've got the force F equal to 240 acting at 60 degrees to the horizontal. Now, in terms of tension now, since this block is being pulled by the horizontal component of this force in this direction, this string is attached to another mass, 25 kgs. It means the tension in this string, in terms or with respect to the 15 kg mass, will be acting in the opposite direction, like that. Because then this mass of 15 kgs is being dragged by this 25 kg mass. So the tension will act in the opposite direction if we are considering the 15 kg mass. When considering the 25 kg mass, this 25 kg mass is being pulled by this string which is attached to this mass, where this mass is being, in turn, is being pulled by this force of 240 newtons, the horizontal component of this force of 240 newtons. So it means since this mass is being pulled by this string, the tension will act towards the right. Okay, I hope that makes sense. So with respect to the 15 kg, the tension is acting in the opposite direction since it's being dragged by this 25 kg mass. Then in terms of the 25 kg mass, which is being pulled to the right, the tension will act towards the right direction. Okay, so now in terms of my force diagram, this is what it looks like. However, the question says we need to draw a free body diagram for each block. So we'll consider each block as individual point masses. So the 25 kg mass, we'll consider it as a point mass on its own, and the 15 kg mass will also consider it as a point mass of its own, like that. Then from there, we're going to then draw the forces acting on the individual point masses based on this force diagram that I have, because now we're drawing the free body diagram. Remember, the free body diagram, your block is considered to be a point mass. So I'll have my tension to the right, and then to the left, I'll have my frictional force. Okay, then vertically upwards, I'll have my normal force, and vertically downwards, I'll have my force due to gravity. Then for the 15 kg mass, I'll have my tension acting in this direction. Then I'll have my force due to gravity acting vertically downwards, and my normal force acting vertically upwards. Then I'll have my force at an angle of 60 degrees acting in that direction there. Okay, so now I've drawn all the forces acting on this object here, of which we must not forget that we've got this kinetic coefficient of friction, which means that there's a frictional force acting on the two masses. So with the 25 kg mass, we have already included that frictional force. However, with the 15 kg mass, we have not included that frictional force. So it means we need to also draw an additional arrow in this case, which will represent that frictional force acting on the 15 kg mass. So then we're going to have another force. In this case, this will be your frictional force. So then now we can then label the two forces. So this will be the force applied, or the individual forces. This is the force applied. This will be normal force, Fn. This is Fg. Then this will be our tension. Then this will be our frictional force F with a K, because then this is kinetic friction, like that. Then here to the right, we'll have our tension. Then we'll have our normal force, Fn. Then down here, we'll have our force due to gravity. Then to the left, we'll have our frictional force, F, small letter F. Okay. So this is how your free body diagram would look like. So question number 2.